Hello class and welcome to Historical Geology. Today I'm going to look at the Plate Tectonics Lab, and I've already downloaded the lab onto my laptop here. And the first part is kind of just some introductory material. Make sure you read through this. I know this question is on the exam. Make sure you know the answer to that one, those 3 points there. I also have this bit about Harry Hess. I know that on the exam I talk about, or at least on my lectures, I talk about Harry Hess. And Harry Hess is important. In fact, I'm going to do my document camera here. Remember, I had 3 criteria for Harry Hess and his seafloor spreading hypothesis, right? And that first was the young seamounts and geos. So remember, the geos are the flat-topped seamounts that were once former islands. He was wondering where all the old ones are, right? And then the other one was the sedimentation rates in ocean basin. And based on what we see on continents, if oceans were as old as continents, the amount of sediment going in there should have piled up to 20 kilometers. And of course, we only see about maybe 500 meters of sediment. So that was a problem. You know, something's going on with the oceans. All the old seamounts are gone, and there's not enough sediment in the ocean, right? Because something's going on. And then the third one was the slow seismic waves under mid-ocean, at mid-ocean ridges, right? So the mid-ocean ridges, he predicted that earthquake waves would slow down because the rock is weak. It's partially molten, so there would be this slowdown, right? So anyways, review that. I do talk about that, and I know I asked these 3 questions on exam 1, right? So that's a little bit about what's going on there. Let's go back to the PDF here. And so again, you'll review this. This is a good figure, right? A couple of key points to point out here is this subduction zone and how the earthquakes get deeper along the subduction zone, because really it's a fault. It's like a reverse or thrust fault. And that reverse or thrust fault, you'll see the deeper and deeper subduction zones. Remember, that's marking that Benioff zone. So remember the Benioff zone. And then the other one, the key thing is that note that we're seeing the lithosphere includes the crust plus the uppermost mantle here. So in this case, if this is ocean crust, the moho would be there. So this is all uppermost mantle or mantle lithosphere, as we know it here. And then the decompression melting at mid-oceanic ridges, hydrous flux melting at about 100 kilometers, see that, there's that magic number, down here in subduction zone. So review your notes on that material there. Some good background information on different plate boundaries. This is a good figure that we compare our observations with in this lab. Note that the East Pacific rise of mid-oceanic ridges, note that it has pretty rare, actually a really fast spreading rate, 13.4, and those are in centimeters per year. And then whereas the mid-Atlantic ridge over here is only around 2.5 to 3 centimeters. So much faster spreading rates in the Pacific Ocean basin. And also these symbols, transform faults, that's kind of like the San Andreas, that side-by-side strike slip type motion. Whenever you see this line with teeth on it, those barbs, that's a convergent margin. So that's where all the subduction zones are going to be. And then the divergent boundaries here, they have 2 arrows pointing away. All right, so you can review that. So this first part for activity 1.1, this is pretty straightforward. I'm not going to really go over this. Make sure you review your lecture notes, and you can answer these questions here, and you can read the different rates right off the map here. The first exercise here for activity 1.2, we're going to have to trace these figure 3 here, and that's this figure here. And I did that, and the way I did it, I just put a piece of paper over my computer screen, or you can do it over the printout. And I put the paper up against a window, and I can trace it out, and you can see that I have those figures over here. So what I did, I traced these shorelines first, as it's asking, and I did it against the window. Now you can move these around, right? And then you're supposed to say, well, if I match these, I see, at least if I'm just doing the shorelines. Remember, the shorelines are the edges of the land, right? Remember, the true edge of the continent isn't till out here, and those are the continental shelves. So you can see in my tracing here, this is just tracing the shorelines, right? Later on, we'll be doing the continental shelves, which is a true edge of continents. And so you can see that there's a pretty substantial gap down here off of South Africa and Argentina over here, right? So that's one of the problems. And then I also trace the continental shelves, right? So I actually went all the way out here to the Falkland Islands, Islas Malvinas, and I have it over here. So now when I rearrange this, I see it's, I still have a gap down here, but it's certainly better than it was when I was only doing the shorelines, right? So it's a much bigger, wider gap. So I kind of fill it in with by using the continental shelves. And that's kind of the whole purpose of this activity 1.2, is that the true edge of the continent are the continental shelves. All this is really underlain by granitic type rocks, continental rock. Basalt, ocean rock, is going to be out here in the ocean basins, right? So that's something you want to cover for this part here. All right, so the next part here for activity 1.3 is kind of the same deal. It's going to talk about these climate zones. And that's one thing that Alfred Wegener looked at in the early 1900s. He saw that certain rocks, certain fossils would form in particular latitudinal positions, climate zones. So we have this, in fact, he was more of a meteorologist, more of an atmospheric and scientist rather than a geologist. That's why we're so interested in the glaciers, right? So you can see polar regions, you're going to have glaciers, up at higher latitudes, around 60 degrees. Subtropical deserts around 30, so lots of sand dunes, lots of sun. And then the tropics around the equator, and kind of the same thing happening up here in the northern hemisphere. So this is kind of just a review of these climate zones. So here they're asking us to kind of cut out this little paleoclimates. In fact, here I say to trace it. You probably don't have to trace it. Yeah, here I say to copy the landmass of the climate zones and on tracing paper. You probably don't have to trace it, but you can just cut these out. You can probably just cut these out. I went ahead and traced mine. And so what you're supposed to do here is you're supposed to take these and then move them around on here to see where they best fit, right? So here's so for example, these glaciers, we know they need to be down here in the colder latitudes, right? Down here farther, down around 60 degrees or farther south, right? So we'll put Africa and South America down here. And then that kind of makes sense because now we have dunes in the arid climate region there, and then we'll have the tropical regions up here closer to the equator. So that kind of fits there. And then for the northern hemisphere, same idea. We'll bring this down here to, in fact, North America seems to have been south of the equator here, and we'll fit these guys in there. So you kind of play around with this. Again, make sure you take a picture of your particular format, right, or whatever you decide to arrange these in, and then submit it with your lab. And also, you're going to want to take a picture of your reassembled South America and Africa coastlines as well. All right, so that's a little bit on what you want to do for that activity. This next one is on paleomagnetism. So, this was kind of the final piece of evidence that really brought all geologists pretty much, into accepting the plate tectonic as a scientific theory, and because it explains so much of what we see. It was you can test the predictions, and sure enough, this is what we found out. So make sure you read about the intro here, and then we have these crons. Your book talks quite a bit about these, so you can review that. I mentioned them a little bit in my lectures, but the key thing is knowing about this idea of normal and reverse polarity. If the rocks have the same polarity as Earth's current polarity, you're going to have a positive anomaly. If they're opposite, if the rocks are opposite, then you're going to have a negative anomaly. And we're using an anomaly because when scientists first discovered that the seafloor had these magnetic signatures that were opposite from what we should expect, they were anomalous. So we started calling these anomalies, right? So in this case, we're going to be doing some measurements. We're going to be measuring and figuring out rates of seafloor spreading. So we're going to examine the magnetic stripes on figure 9, and that's back over here, right? So that's just figure 9. And they're asking us in this first question, are there, what's the orientation of these? And you can see that they're going to be parallel. right? They're parallel to the mid-ocean ridge axis, right? They're all parallel. So here we want to say, you know, you could just circle parallel or write the word parallel here, right? So they're going to be parallel to that mid-oceanic ridges, which is a strong indication that, you know, this seafloor out over here was once here and has since moved away to its current position, right? And obviously, for mid-oceanic ridges, you know it's young here and it's old farther away, right? So these two darker stripes are the same age and they used to be here and have since moved to their current position. Same thing can be said with the Juan de Fuca Ridge out here off of Canada. Now, they're also talking about describe the relationship between ages. Oh yeah, so, you know, I just did it right here. Explain how the process they produce. So here I just kind of want you to review from your readings or from what you've gleaned from my lectures, try to explain what's going on here. Let's see, some magnetic stripes are wide. Yeah, so if they're wider or slower, there's a couple of things that could be going on. One, you could be seeing a faster seafloor spreading rate, right? So the, you know, we could have faster seafloor spreading. So we're producing more basalt lava, and we're making these magnetic stripes wider. Or the other thing that could be happening is we have a longer duration of a certain polarity, longer duration. So instead of just, you know, longer duration of polarity. I think I mentioned in my video lectures that these magnetic reversals occur about every 500,000 to 700,000 years, but some can last 1.2 million years or 3. So they you know, we don't know how often exactly they occur. On average, it's 500,000 to 700,000 years, but some can take much longer, some can be much shorter, right? And that's just a testament to what we're seeing here. You can see that this Matayama Kron, it was a much longer duration than the Gauss down here, right? That's a short one, right? So you can see that can also help explain the width of these magnetic stripes here, right? Now for activity 1.5, here we're going to be looking at figure 3. We're going to be measuring some distances. So here's figure 3. So they're going to ask us to measure along a fracture zone that's pointed out by an arrow here, right? So that's this fracture zone here. You can see that this fracture zone basically starts right here in Africa, and it'll go out over, and you want to measure to there. So remember, we're measuring from continental shelf to continental shelf, right? So that distance there. And then we have a scale here, right? So that's going to help us there. So what I'll do, I'll see that this distance, and I can kind of curve this, is about 2.6 inches. So if I put this up here, so there's 2.2, which is 800. And so if I put that at 2.2, I go to 2.6 right here. So that's maybe 150. So 800 plus 150. So this distance is about 950 kilometers. Maybe you got a better number, but you know, if you get 950, 1,000, it doesn't matter. Somewhere along that line, because your rates should all be sort of similar. So then they're going to ask us here. So we got 950. So we just figured that out. So that's right. We'll put here. We'll put 950. So here, the oldest rocks are 120 million years old. So calculate the rate of spreading, right? So to do this, we're going to take that. Remember, the rate is some distance over time. And so our distance was 950 kilometers, and our time was 120 million years, right? So it's going to be kilometers per million year, right? So, well, that's the first option right here. If we take the 950 and divide it by the 120, we get 7.9. So we'll just make it 7.9 kilometers per million year. So every million year it moves about 7.9. They're asking us to make it into kilometers per. You know, take this number 7.9 and you divide it by a million, because this is a million, right? So we're going to take that and we're going to, let's just make it 7.9, and we're going to divide it by 1 million. 1, 2, 3, 1, 2, 3. It's going to be a really, so we'll make it, let's see, 1, 2, 3, 4, 5, 6. So 7.9 times 10 to the minus 6. 7.9 times 10 to the minus 6. So it's a really small number, right? 0.000079.